welcome to your first Statistics 310 video lecture. My name is Eric Merchant, and I'll be a guy you'll be looking at a whole ton this term. So anyway, I wanted to start off today with a little bit of a review about one of the central math concepts that we're going to be dealing with in our statistics course, and that is the concept of a function. So to define a function, all I have to do is tell you, okay, here's a function, and when you plug in a number x, here's what you do to that x to get the function's value. A function is essentially a kind of machine where you plug in one kind of number and you get another number out. The important thing is, this machine has to, if you plug in the same number each time, you should get the same number out every time. And if we can write it as an equation, then that's definitely going to be the case. So, one of the ways we talk about functions, for instance, is to just write a table of possible x's, and see what sort of y values or outputs we get out. So, easy enough. Here's an x, and here's what f of x gives us. So, for example, with our function here, if x equals 0, then f of x will equal 3 times 0 plus 4, which will equal, 3 times 0 is just nothing, so that's just going to equal 4. And then if we plug in 1, we get 3 times 1 plus 4, which is apparently 7. And we can continue this table. 2 will give us 10, 3 will give us 13, ... This is not the most efficient way of representing a function, because this is just saying for whole numbers, and I happen to start at 0 in this case, these are my outputs. So, a more interesting way to look at functions is to take a look at them as points on a graph in the coordinate or plane system. So this is a perfectly nice list. Let's take this list and see what it looks like as a picture. So if I start here and here, the vertical line, the x-axis, will represent the inputs I'm putting in, and the y-axis we will have equal to the function values that we get out. So if you start at 0, you get a number like 4 right here. And when I plug in x equals 1, I get 7 up here. And then we see that actually if you plugged in negative 1, you would get 1, because negative 1 times 3 is negative 3, and adding 4 gives us an output value of 1. And what you start to notice is that this particular equation gives us a straight line that goes like this. And this then gives us an idea of maybe some other values of this function. So for example, it looks like if I plug in 1/2, the picture tells me, oh, I should be about halfway between 4 and 7, or about 5.5. So anytime you have a function of the form f of x equals mx plus b, it is the case that you will actually have the equation of a straight line. That is what the graph is going to look like. And these two numbers come into play too. So this 4 says, if you plug in 0, you're going to multiply whatever times 0, and then you're going to get just this number here that you add there. So this is 4, this is what we call the y-intercept, because this is where the line hits the y-axis. Now you'll notice, where does the 3 come in? Well, notice as I start at x equals 0 and 4, and then I move over to x equals 1 and go up to 7, that's actually telling me what we call the slope of this line. This tells me that when I increase x by 1, notice I increase y from 4 to 7, which means I increase y by exactly 3. This is called the slope because this right triangle I just drew has legs size 3 and 1. And hence the slope tells us the ratio between, if you increase x a certain amount, how much will you increase y? If you increase x by 2, you will increase y by 6, etc. So that's all fine and good. The theory of lines is completely well understood. Just tell me where to start, 0, comma, whatever this number is, and then tell me how far up to go every time you go across. Sometimes lines don't go up like this. They could actually go over and down. this would be a line with a negative slope. So every time you go over 1, you would actually go down, and the equation for this might be something like f of x equals negative 2x plus 3, or something like that. So that's fine. Functions have many ways that you can write them. You can write them as an equation that will tell you literally the mathematical instructions for given an x, what sort of output you will get. You can write down a little table that actually helps you get sort of familiar with, oh, what's happening with this function. As I increase my x's, my f of x's increase even bigger. And then you can take a look at this picture and go, oh, now I see what's going on. I start at 4, and as I move over 1, I go up 3 each time, and then hence I have a straight line. Of course, not all functions are straight lines, so let's take a look at some more slightly interesting functions. So if I have a somewhat more complicated equation, so suppose I say, all right, I'm going to give you an f of x, and it's going to be equal to x squared. So this means, remember, squared means multiply x by itself. So this is just x times x. And you can plug in some values, see what you get. Start with 0. 0 times 0 is, oh, right, 0. And then 1. 1 times 1 is 1. And 2 times 2 is 4. And then 3 times 3 is 9. And so these numbers are actually increasing. But notice, unlike our last example, the numbers aren't increasing at a constant rate. When I go from 0 to 1 in x's, I go from 0 to 1 in f. And when I go from 1 to 2, all of a sudden I go from 1 to 4. And then when I go from 2 to 3 in my x values, my y values are increasing from 4 to 9, so that's an increase of 5. So this, like the last one, is an increasing function, but it's increasing sort of faster and faster. So what the graph looks like is this. So that when I'm at 1, I'm still at 1 in my y-axis, but by the time I get to 2, I'm all the way up to 4. So this actually has some curve to it. It is not a straight line. The other interesting thing about this is, what if I try plugging in negative x's? So you might remember that when you start with a negative number and you square it, you get back another positive number. Negative times negative gets you back to positive. So this one, I plug in negative 1 and I get 1. Plug in negative 2 and I get 4. And what we see is that the function looks, it's a mirror image of the other one. This is called an even function because if I plug in a negative number, I get exactly the same result as had I plugged in the corresponding positive number. So this is not a straight line because it is not of the form ax plus b. It is in fact asking you to do something more complicated with x and multiply it by itself. Now in statistics we're interested in a bunch of different functions, but the ones that are going to be really important are the ones where the area under the curve sums up to 1. And that's because in statistics or probability, there's a 100% chance that something's going to happen. Either it's going to rain or it's not, either your coin's going to come up heads or tails, etc. So let's look at a very, very basic function and see what the area under it can tell us. So if you take the function f of x equals 1/4. Now a lot of people get confused because there's no x there, but that just means this is a really boring function. That means any x you plug in, I'm going to spit out 1/4. That's what this function does to that x. So if you give me x equals 0, it's 1/4. If you give me x equals 5, it's 1/4. If you give me x equals 100, it's always 1/4 coming out. And I'm actually going to say that this function is only defined for x's between 0 and 4. So I write that this way, right? Okay, my x, any x you give me, has to be greater than or equal to 0 and less than or equal to 4. So I'm restricting the function. The input values we care about are things that are only run from 0 to 4. And so here's what the graph of this looks like. It's just as boring as you think it is. Right at 1/4, I start with my line at 0, and then I go out to my line at 4. This is a rectangle. This forms a little rectangle right here like this. And so this is a rectangle of height 1/4 and width 4. The width of this rectangle, because this rectangle runs from 0 to 4, is 4. So that means the area inside this rectangle, the area equals 1. And what that allows to tell us, what that tells us is, we can use this as a probability model. If something falls between 0 and 4 and it has the exact same probability of falling in any place in this region, then that tells us we're dealing with a constant probability function. And the probability of falling in some smaller region inside here is exactly the area that's taken up by that smaller chunk of area. So let me show you what I mean. If you said, okay, I'm plugging in numbers from 0, and I'm getting 0 to 4, what's the probability the number I start with is between 0 and 2? So this tells us right here, since we can take 2 and then shade in the area of the rectangle between 0 and 2, this looks like, and in fact is, about half the rectangle. So we say, okay, the probability that your x value is going to fall between 0 and 2 is exactly half of it, because that takes up half of the rectangle. So we write this probability that you're given an x that falls between 0 and 2 is equal to 1/2. And so the geometric area embedded in this shape tells us information about the probability of events happening with this probability curve. Now, of course, most probability functions aren't this straightforward, aren't this flat. Usually some things are more likely than other things. So the kind of functions we'll be looking at over the next 8 weeks usually have shapes like a bell curve. Or any old thing. We're going to look at a ton of stuff, but here's one you might see. So if you had, what's the temperature going to be tomorrow? It turns out that, well, most tomorrows are at about 62 degrees. But certainly some of them can be as cold as 45 degrees. And sometimes we get record heat like over at about 80 degrees. So what the probability curve of that would look like is taller at 62 than it would be at 45. So we would start here, and it would make sort of a bell curve that tapers off. And this bell curve tells us, okay, most of the data is going to be in here near to 62. But sometimes you have a crazy cold day, or you have a crazy hot day, and that can happen. So what are the odds that it's going to be exactly 62? Well, that's a tiny little sliver here. But what are the odds that the temperature is going to be, say, between 58 and 64? We can actually deduce that, calculate it, by looking at the area underneath the curve between those two endpoints. And if we were looking at some equation, hopefully we'd have some way of saying, well, here's the probability, here's the area there, and then some way to actually compute that, but later for that. Also, there are other questions you might ask. You might say, well, I'm going to go to the beach as long as it's 55 or more. This is Oregon after all, and 55 would be a great day at the beach. So you'd want to say, well, what's the probability that the temperature is going to be less than 55? So we'd find 55 on our x-axis, and then shade everything below it. And that chunk of area represents the probability that the temperature is going to be below 55. Notice this gets very, very close to 0, but in most cases it doesn't actually hit 0. It's not impossible that it's going to be 32 degrees. It's just unlikely. It's not impossible that it's going to be 100 degrees. It's just fairly unlikely. So, in terms of our use of graphs and functions, we're going to be interested in a very, very specialized subset of the world of all functions out there. And this subset will be called probability curves. And this is our goal, our immediate goal, in terms of what to understand about functions, what they look like, what they tell us about how the world interacts with us. So anyway, I hope this has been helpful, and I'll be back pretty soon to give you guys your first Excel lesson. So we'll see you then. Thanks.